Hi guys, welcome to the next lesson. This is chapter 3.3 from Text and Text 6, Dividing Complex Numbers. We're going to be looking at questions 4, 5 part 1, 6, 8, 9 and 12 part 1 on pages 104, 105. We'll just jump straight in. We looked at adding, subtracting and multiplying complex numbers in the last chapter or in the last section. It wasn't really too different to anything we've done before, but these are a brand new type of number, and it turns out division doesn't work so well for them. We can divide numbers like say 3 plus 6i divided by 3 because you've got a common factor of 3 there. You can divide real numbers into complex numbers quite easily. That's just going to be 1 plus 2i. But if you're asked to do something like down here where we're dividing by a complex number, it's a bit more tricky. It exploits a thing called the conjugate or the complex conjugate. Now we've met the conjugate in surds before in algebra, but for the moment, for the complex conjugate, what you're looking at, if z is 2 plus 6i, z bar, which is the symbol we use for the complex conjugate, is 2 minus 6i. And this will use your difference of two squares expansion to make the I parts disappear. So it'll mean that we end up with a real number in the division anytime we want to do that. That's what we're going to be working towards. Just to show you what I mean by that, let's have a look. Question 4, part 1 tells you z is this number here, 2 plus 6i, multiply z by z bar. Okay, so z by z bar is 2 plus 6i multiplied by 2 minus 6i. And when you multiply that out, 2 by 2 is 4. 2 by minus 6i is minus 12i. Plus 6i by 2 is plus 12i. And 6i by minus 6i is minus 6i squared. Okay, so these parts disappear. That's just 0. And you're left with 4 minus 6 times minus 1, which is 4 plus 6. So the answer there is 10, which is a real number. So questions down here where you multiply, like this one, where you multiply top and bottom of your fraction by that complex conjugate, you'll end up with a real number at the bottom, which we know how to divide with. Just to show you what happens, question 4, if you add a number to its complex conjugate, so 2 plus 6i plus 2 minus 6i, you get a real number as well. But of course you can't do that top and bottom of a fraction, so it's not that useful to us in terms of division. If you subtract 2 plus 6i minus 2 minus 6i, just put that in brackets because the minus operates on both. Probably should have done it up here as well. 2 minus 2 is 0. 6i take away negative 6i, that's plus 6i. So you're left with 12i, so you're left with an entirely imaginary number when you subtract an entirely real number when you add. Z squared, I'm not sure why that's there. That's just 2 plus 6i times 2 plus 6i, which is 4 plus 12i plus 12i plus 36i squared. Excuse me, up here, how embarrassing. 6i by minus 6i is minus 36i squared. So that's 4 plus 36, which is 40. Okay, sorry about that. Anyway, what's that going to be? 4 plus 24i minus 36. So that's minus 32 plus 24i. I suppose what I'd like you to pay attention to is that part there, the complex conjugate. That's what we're going to be using when we're asked to divide, like in question 5. So question 5 asks us to simplify this fraction. So on the top, it's not hard, that's 5 plus 5i, and on the bottom we've got this 4 minus I. And we say, well, how do we divide by 4 minus I? And the fact is we can't. Okay, we can only divide by real numbers. So I'm going to make the bottom number a real number. Okay, so that's by multiplying by 4 plus I in the bottom and 4 plus I in the top. So our rule with fractions, multiply top and bottom by the same number. That's okay. So what are we left with? Well, on the top, 5 by 4 is 20. 5 by I is 5i. 5i by 4 is 20. I and 5i by I is plus 5i squared. On the bottom, 4 by 4 is 16. 4 by I is plus 4i. Minus y by 4 is minus 4i. And minus I by 1 is, minus I by I is minus I squared. So 20 plus 25i minus 5 on the top divided by 16 minus 1. So that's going to leave us with 15 plus 25i divided by 17. Okay, and then that's 15/17 plus 25/17 of I. Okay, so there's your answer to 5 part 1. But maybe more importantly, here's your method to get rid of a denominator that is complex. Multiply top and bottom by the complex conjugate, in this case 4 plus I. Question 6 tells us, question 6 says, find the values of x and y in each of the following. So in the first one, this exploits the idea that if you have one complex number equal to another complex number, well, the only way for that to happen is if the real parts are the same. So x has to be 4 in part 1, and for the complex parts to be the same. The imaginary parts, excuse me, to be the same. So y has to be minus 2. So the answer there is x is 4, y is minus 2. It's a bit trickier in this one here, so I've got that one ready to go. X plus yi equals 2 plus I times 3 minus 2i. So if we multiply that out, we're going to get ourselves 6 minus 4i plus 3i minus 2i squared, which is 6 minus 1i plus 2. Okay, minus 2 by I squared. That's going to be plus 2. So that's going to be 8 minus I. And therefore x has to be the real part, 8, and y has to be the imaginary part, minus 1. Okay, because yi and minus 1i have to be the same, so y is minus 1. This one here, same as we've seen before, we've got a denominator there that is complex. We don't like it. So to get rid of it, you're going to multiply top and bottom of your fraction by the complex conjugate, which is 2 plus I. 2 plus I. Okay, so what's that going to give us? 7 2s are 14. 7 times I is 7i. I times 2 is 2i. And I times I is I squared. All divided by 2 by 2 is 4. Plus 2 by I is 2i. I by 2 minus I by 2 is minus 2i. And minus I by plus I is minus I squared. So we are going to get ourselves 14 plus 9I minus 1 over 4, that's going to disappear, plus 1. Okay, so we get ourselves 13 plus 9I over 5 is our answer there. Which means x has to have been 13 over 5, and y has to have been 9 over 5. This last one, squaring, well, that just multiply by itself, so that's 2 minus 3i times 2 minus 3i, which is 4 minus 6i minus 6i plus 9i squared. Okay, 2 by 2 is 4, 2 by minus 3 is minus 6i, minus 3 by 2 is minus 6i, minus 3i by minus 3i is plus 9i squared. So that's going to be 4 minus 12i minus 9, which is minus 5 minus 12i. Question 8. If z is this number here, And this rule here is true, that 3 times z minus 1 is equal to I times 3 plus I. They want you to find the values of x and of y. So same idea here, real parts equal real parts, imaginary parts equal imaginary parts. So 3z, instead of z, we're going to stick in our x plus y I. Minus 1 equals I times 3 plus I. Multiply that out, you get 3x plus 3yi minus 3 equals 3I plus I squared, we'll say. Okay, but that of course is the same as 3I minus 1. Okay, so real parts have to equal real parts. That means 3x minus 3 has to equal, the real parts over here are minus 1. And imaginary parts, 3yi have to equal imaginary parts 3I. Okay, so that's very easy. Y has to be 1. And over here, if you move that across, 3x equals minus 1 plus 3. 3x is 2. X is 2 thirds. Okay, so there's question 8. Question 9, based around that same idea again, a little bit more sophisticated. There's z1 is minus 3 plus 4i, z2 is 1 plus 2i. So this rule holds z1 plus some number p plus iq times z2 equals 0. Okay, and the question is find p and find q. There it is there. P and Q are real numbers. Find the values of P and Q. They give you this hint that 0 equals 0 plus 0i. That is to say that this has a real part of 0 and an imaginary part of 0. So multiplying this out, or sorry, substituting in 3 plus 4i plus P plus iq times 1 plus 2i equals 0 plus 0i. That's going to say minus 3 plus 4i plus p plus 2pi plus iq plus 2qi squared equals 0. So it's a lot busier than the last one, even though it's the same idea. Where do we go from there? Minus 3 plus 4i plus p plus 2pi plus iq minus 2q equals 0 plus 0i. Okay, so our real parts, minus 3 plus p minus 2q equals 0. And our imaginary parts, 4i plus 2pi plus iq equals 0. Okay, so that gives us two simultaneous equations. This first one I'm going to write as p minus 2q equals 3. And this second one, when the i's cancel, is 4. It's 2p plus q equals minus 4. Okay, so I'm going to call that A, call that B. I'm going to find another page. So our first equation, p minus 2q equals 3. And our second equation, 2p plus q equals minus 4. So to solve that, I'm going to take this top equation and I'm going to multiply it through. I'm going to take the bottom equation, multiply through by 2. Okay, so that's going to stay as p minus 2q equals 3. And this one, I'll write it up the top, is going to say 4p plus 2q is minus 8. So when I put them together, I'm going to get 5p plus 0 equals minus 5, which means p has to be minus 1. And then I can come back to any of those equations. This one here, that becomes minus 1 minus 2q equals 3. Minus 2q then equals 4 when I bring the minus 1 over. And q is 4 divided by minus 2, which is minus 2. Okay, so there's my answer. PQ, actually I write P plus QI is going to be minus 1 minus 2I. And lastly, let's have a look at question 12, which is kind of a tricky-ish type of question. Find the square root. Now later on we'll see other methods for finding the square roots of these numbers. It's a really key part of this branch of mathematics, but here's the method we're going to use for the moment. We're going to say, well, it has to be x plus yi. It has to be some type of number. And if it's a real number, well then your y will be 0. And if it is a if it's a complex number, you've got it covered there. Well, how do I get rid of that? Square root, I can square both sides of the equation. So that squared is just going to be minus 12 minus 16i. This side squared is going to be x plus yi times x plus yi. If you're familiar with the expansion, it's square the first, square the second, twice the product. If you're not, well, just multiply that out whatever way you normally would, plus 2xyi. So what we get from that is that minus 12 minus 16i equals x squared minus y squared. That becomes minus y squared because of the I squared is minus 1, plus 2xyi. Real parts have to equal real parts. That means minus 12 has to equal x squared minus y squared. And imaginary parts have to equal imaginary parts. That means minus 16i has to equal 2xyi. And this straight away gives us minus 16 equals 2xy, minus 8 equals xy, and if you like, y equals minus 8 over x. Okay, the reason I'm doing that, if you know how to do this type of thing, this is a substitution. Okay, you've got one linear equation, one quadratic, and they're simultaneous equations. They're true at the same time. So I'm going to carry that on and say if y minus 8 over x, if that's y, then y squared is minus 8 over x squared, which is 64 over x squared. So coming back over here, we get minus 12 equals x squared minus, instead of that, y squared, we've got 64 over x squared. And these get a little bit messy from here if you try and keep working with x squared. So I'm going to make up a new variable a for x squared. And hopefully you'll see that this 64 over a can be rewritten this way. The benefit of that is just what I'm about to get will look like a quadratic that you know how to work with. So multiplying through by a gives me minus 12a is a squared minus 64. And then that's going to be 0 is a squared plus 12a minus 64, which factorizes as a and a. Factors of 64 that add to 12. 16 times 4 is 64, so 16 and 4 plus 16 and minus 4. That'll do the job, which means a equals 16 or a equals 4. But remember, a was just another word for x squared. So x squared is minus 16, or x squared is 4. So in this case, x equals plus 2 or x equals minus 2. Here we get x equals 4i or x equals minus 4i. We can ignore that for the moment. Well, we can ignore it outright. I'll tell you why. Up here, and maybe I should have said it, x and y have to be real numbers. Okay, which is one of our conditions for complex numbers. So x is a real number. It's either 2 or minus 2. Y, remember, is minus 8 over x. So if x is 2, y is minus 8 over 2, which is minus 4. So one possible solution is x plus yi equals 2 minus 4i. The other one is that x plus yi is minus 2, and then if x is minus 2, y was minus 8 over minus 2 is plus 4. So minus 2 plus 4i. So we got two solutions here, and we'll see that quite a lot. Complex numbers have two square roots. In fact, all numbers have two square roots, depending on your definition. Okay, thank you very much. What I'd like you to do tomorrow in class, please, page 104, 105, questions 2, 3, 5, 7, 10, 11, and 13. And if you can be ready to start as soon as you come in. Thank you very much.